Good morning or good afternoon from everywhere you are listening from. We are looking at simple harmonic motion. Learning objective at the end of this lesson should just be able to explain the concept of simple harmonic motion or stylish state example of it. Then define the term relating to simple harmonic motion, such as the period, the frequency, and amplitude. Then solve simple problem relating to period, frequency, and amplitude, as well as the energy stored in simple harmonic motion. Taken. All right. Let's look ahead. What do you understand by simple harmonic motion? Just as we can see from a guitar string, such an example, where we play the guitar and it move forward and backward on a straight line, making such of noise or sound being produced. And simple harmonic motion is a periodic motion of a body along a straight line such that the acceleration of that body is directed towards a fixed point and is proportional to its displacement from that point. All right. Taking the terms relating to simple harmonic motion are period, frequency, and amplitude. Here we look at what is period. Period, which symbolize T there, is the time required to make one complete revolution about a point of reference, and it is measured in seconds. Time can be given in different dimensions, but we are looking at time being t is equal to 2 pi root L over G. L there the length and G acceleration due to gravity. And time can also be given t is equal to 2 pi root m over k, where the m there stands for the mass of the object, and k there is stand for our stiffness or constants of proportionality, as we can see from Hooke's law. All right. T is equal to the time taken and over the n, the number of revolution that the object make. All right. And t can also be what is a reciprocal of what our frequency, as t is equal to 1 over f. So whenever we have any equation to do with, once we understand the concept of our time and relation to other values, then we can actually get time in that problem. Frequency, this is the number of complete revolution per unit of time. It is measured in arcs or per second, and is also denoted with letter f. F is equal to 1 over t, or we say what f is equal to n divided by the time. Okay. Then the amplitude, here we said amplitude is the maximum displacement of the body from the equilibrium position, and it is measured in meter. So whenever we have the amplitude to demonstrate in any equation, remember to its unit is meter. So whenever you are given in centimeter the amplitude, try and convert it to meter. If it's centimeter, divide by 100 and you get your meter. Okay. So energy stored in simple harmonic motion. Energy stored from the diagram above, you can see there are three dimensions at which what this the three ways in which this the point that this spring is made. You can see the one in the middle, and the one at the top right, and the one at the top left, swinging to and fro. Now the highest point that is making at your right hand is what we call what the when the object is making what the maximum potential energy, that is at maximum potential energy. Therefore at this point the kinetic energy here is what is equal to 0, and also there is no velocity movement there. That means what the velocity at this point is also what is 0. But at this lowest point that we are looking at, we say what the kinetic energy is what is at maximum, because there is what that is where the point of what action is being taking place. There's movement, and this point we have it was as the our midpoint, where the kinetic energy here is what is maximum, while the potential energy here is what is equal to 0, is equal to 0. Now in order to calculate the energy in a simple harmonic motion, we said what it is necessary to calculate both the kinetic energy and potential energy of that particle, in which what that particle possesses. Now the kinetic energy of simple harmonic motion, we said what is the energy the body possesses when it's in what in motion, and the instantaneous velocity, which is a v of that object performing the simple harmonic motion, at a distance x from the mean position will be given as v is equal to omega root a square minus x square. Now the v here we say what is the velocity, while w represent what our angular velocity, then root a square, a our amplitude and our x our distance. Now from our kinetic energy, since kinetic energy is equal to what half mv square, we look at what, since we are squaring both sides of our equation of velocity, instantaneous velocity, when we have of v square is equal to omega square bracket a square minus x square, which we have taken the word the root away to make it what square, then we can now substitute our value of v square in this our equation of kinetic energy, which is what k E is equal to half mv square. So our v will be given, instead of putting our v square, then we now put what it is equal to there too, which is what w square is equal to a square minus s square. So as we can see, we have a k E is equal to 1 over 2 mv square bracket a square minus x square. Now we've already know that our w is the angular velocity and the a there representing the amplitude and x is the distance. Now since w omega is given as omega is equal to root k over m as our constant, which is constant of proportionality of our stiffness divided by mass, then when we square both sides we have what omega is now square, then our root can be removed, then we have omega square is equal to what k over m. Now when we substitute for omega square in the equation under kinetic energy, which we have k is equal to 1 over 2 m omega square bracket a square minus s square, then we have what k is equal to k divided by 2 bracket a square minus s square. So in this, in any form, if you are given the k, our stiffness, then you can know how to calculate what our kinetic energy. Now let's look at potential energy. We said potential energy is the energy possessed by the particle when it's at rest. And in this, when we look at the spring, we always have the maximum, and we have P E is equal to what half over k a square. Now the a here is representing what our amplitude, and k is telling us about what the constant of proportionality, which is also what refers to our stiffness. Now to calculate the total energy in a simple harmonic motion, it is given as what the sum of this potential energy plus the kinetic energy. As you can see, let's look at quickly example of how we can solve this kind of simple equation. Now a mass of 5 kg is hung from the end of a coil spring of the system is made to vibrate with simple harmonic motion of period 4 seconds. Find the force constant of the spring and the energy if the amplitude of the vibration is 3 centimeter. Now looking at writing down all the parameters required here, we have what our mass as well 5 kg, then we are given the time which is 4 seconds, then we are looking for what the constant, then our energy. Okay, then we are given the amplitude, and our amplitude here is what is given in centimeter, therefore we need to convert it to what to meter. So 3 centimeter divided by 100 will give us 0.03 meter. Now the equation that can bind this together in order to get our constant, that is what our stiffness, is equal to what T is equal to 2 pi m divided by k. Good. So when we, what is the value of our T is 4 is equal to 2 pi, then our m mass is 5 and divided by the k. When we now look at this, in order to what to remove the root in this, we square both. So we have a 4 square is equal to 2 pi r root divided by 4k all square. Then when we do this, we have what 4 square gives us 16 is equal to 2 square will give us 4, then pi square will go pi square, then the root is be taken care of, then we have 5 divided by k. Then here we have a 16. When we divide both sides, we have by, when we cross multiply rather, sorry, we have it 16k, then 4 times 5 give us 20 pi square. Then what do? We divide both sides by 16 in order to get our k, the subject of formula. Then k is equal to what? 20 pi squared divided by 16. When we divide it, we have k to be 1.25 pi squared. Taking now, since kinetic energy is given as 1 over 2 ka squared, therefore we know our k and we have our amplitude already. We just have to substitute them inside this equation. Then we have the energy as k is equal to 1 over 2. What's our k? The value of our k is 1.25 pi squared times what's our a? Amplitude is what? 0.03 all square. So when we divide this, we have 0.001125 pi squared divided by 2. Then our k is equal to what? 0.0056 pi square joules. So to this end, we've come to the end of this. If you have any question, please reach out to me. God bless you as we see next class.